What's up? This is Mario, and welcome to Awesome Acoustics. In this video, I want to talk about how the sine wave originates from trigonometry. Our journey begins with a simple right triangle. That is, one of its angles is going to be 90 degrees. The longest side, opposite the 90-degree angle, is called the hypotenuse. Now, if we give one of its other two angles a name, say theta, then the other sides of the triangle get names too. The side that touches the angle is called the adjacent leg, and the side that does not touch the angle is called the opposite leg. A trigonometric function is simply a ratio of two sides of a right triangle when you give an angle to that function. For example, the trigonometric function sine of an angle is equal to the opposite leg divided by the hypotenuse, and the cosine function of the same angle is equal to the adjacent leg divided by the hypotenuse. In this specific triangle, the opposite leg divided by the hypotenuse gives us 0.5. This tells us that the length of the opposite leg is 0.5 times, or half, of the hypotenuse. But if we didn't have the lengths of the sides, and instead we only knew that this angle is 30 degrees, the sine of 30 degrees also gives us 0.5. So, with the angle, here we know the ratio between the sides even though we don't have their lengths. If you want to calculate the functions to confirm the examples, remember to select degrees on your calculator rather than radians. In this example, if we know the hypotenuse, we can obtain the opposite leg. The cosine of the same angle gives us 0.866, which means that the adjacent leg is 0.866 times the hypotenuse. A useful trick is that if we use a hypotenuse of 1, then the sine and cosine functions give us the lengths directly. When we have the angle here, the sine is related to the vertical side and the cosine to the horizontal side. A couple of interesting cases are when we have an angle of 0 degrees or 90 degrees. As we get closer to 0 degrees, we see that the opposite leg starts to disappear. At 0 degrees, the length is 0, so the sine of 0 degrees is 0. As we get closer to 90 degrees, the opposite leg starts to become the same as the hypotenuse. And at 90 degrees, they are exactly the same. If the opposite leg and the hypotenuse are equal and we divide them, it gives 1. Then the sine of 90 degrees is equal to 1. Now, a right triangle cannot have an angle greater than 90 degrees. So, what happens if we plug an angle greater than 90 degrees into a trigonometric function? Well, the opposite leg goes over to the other side. And this triangle is what the trigonometric function sees. Here, the inner angle of this triangle is also 30 degrees. So the sine of 150 degrees gives us 0.5, which is the same result as the sine of 30 degrees. The cosine of 150 degrees would also give us the same number as the cosine of 30, but in this case with a negative sign. This is because we are now on the negative side of the x-axis. If we go past 180 degrees, the triangle flips again, this time vertically. Since we are now on the negative side of the y-axis, then the sine also gives us a negative number. Here, it looks as if we are rotating the hypotenuse, and the legs of the triangle are the coordinates of the point at the end of the hypotenuse. So actually, we are describing a circle, where the hypotenuse is the radius, and the legs indicate the coordinates along the contour. This is the intimate relationship between a circle and a right triangle. If we plot the trigonometric function sine against the angle, what we get is this, which is what we call a sine wave or sinusoid. Here, we can see the cases we mentioned before. At 30 degrees, the sine is 0.5. At 0 degrees, the sine is 0. At 90 degrees, the sine is 1. At 180 degrees, the sine returns to 0. And after 180 degrees, this pattern is inverted. In this animation, we can see how the circular motion and the sine wave can be considered two different projections of a helix. So, one way I like to think of the sine wave is that it's like looking at a circle from the side. That is, one dimension of the circular rotation. All of this may seem very mathematical and abstract, but it can also be observed in real life. Here we have a circle, and if we view it from the side and expand it, we have a sine wave. In a wave, the angle at which it is at a specific moment is called its phase. For example, the only point where the sine function is equal to 1 is when its phase is 90 degrees. Now, let's look at the plot of a cosine. Here, we can see that at 0 degrees, the adjacent leg is equal to the hypotenuse. So the cosine of 0 degrees is going to be 1. And at 90 degrees, the adjacent leg disappears. So the cosine of 90 degrees is 0. This is another animation where we can appreciate the relationship between the circle, the sine, and the cosine. Another way to interpret this is that the sine and cosine are the shadow of the radius on the vertical axis and the horizontal axis respectively. If we extend beyond 360 degrees, the pattern just repeats itself. Here, the cosine looks the same as the sine, just shifted a bit to the left. In fact, we can think of the cosine simply as a sine shifted 90 degrees. This is why the sine and cosine are known together as sinusoids, because both waves have a sinusoidal shape, only shifted in phase. Something interesting is that the phase is individual for each wave. When you plot waves against time or distance, the horizontal axis generally applies to all waves. But each wave carries its own phase axis, since it is related to the cycle of its own oscillation. With that, we conclude this video, and I'll see you in the next one.